We present local, our method for learning object attribute composition using localization. Our goal in this work is to predict unseen object attribute compositions. Specifically, during training, we will see a set of object attribute composition from a list of objects and attributes. For example, our training set could contain a red apple and a rotten orange. Then, during inference, our goal is to predict the composition a rotten apple, which is not seen during training. This task is commonly known as compositional zero-shot learning or CZSL. This task is extremely important for developing robust systems to work in actual ever-changing environment, as there will always be some object attribute compositions that are not seen during training. Exhaustive annotations will not be scalable or even effective for such cases. Existing models that predict the unseen object attribute compositions are based on various graph and attention-based architectures. They perform well in scenarios shown here with one prominent object and no interfering background. However, these models do not make the correct object attribute association when there is a lot of interfering elements and background clutter. Two such examples are shown here. All existing models fail to predict the correct composition, a ripe apple and a blue bird. Our analysis has shown that this limitation is mainly due to the fact that existing models consider every spatial location of the input image homogeneously. In essence, current works do not utilize localized feature learning. We developed local specifically to address this issue. Before going into details, we will give an overview of our network. We have two components in our network, a localized feature extractor and a compositional classifier. From the input image, the localized feature extractor creates localized features that have a high chance of containing an object. This type of feature extraction helps the network to localize the object of interest amongst clutter and background elements. Composition classifier refines these features with semantics to make final object and attribute composition. Our network is trained in two stages. In the first stage, we pre-train our localized feature extractor, and in the second stage, we train the full network with a lower learning rate for the localized feature extractor. Now we will describe the first training step for our localized feature extractor. The localized feature extractor is composed of an image encoder and a proposal generation framework with the region proposal network and an anchor generator. From the encoded image features, region proposals are generated by the region proposal network and anchor proposals are generated by the anchor generator. The text embedder is only used during training to generate pseudo labels for the anchor proposals. Based on these pseudo labels, we bring together regions and anchor proposals with objects of interest close to each other by a contrastive loss. The output of this feature extractor is a set of localized features. These are fed to our composition classifier, which we will discuss next. The composition classifier takes a set of localized features and fuses them together to a generalized feature representation. Then, this feature is refined separately by object and attribute semantics in two refinement blocks. Finally, we utilize fully connected networks to make our final object and attribute predictions. We will evaluate local on three state-of-the-art datasets. Among these datasets, CGQA has more scenarios which are challenging, whereas MIT States and UT Zappos are comparatively simpler datasets with limited background clutter. We report local's performance in terms of seen and unseen class accuracies and the area under the curve or AUC for different operating conditions. In all the three datasets, local significantly outperforms current methods. Specifically, for the more challenging CGQA dataset that has significant background clutter, the effectiveness of our localized feature extractor is clearly demonstrated by its superior performance on the unseen object attribute associations. We additionally test the effectiveness of our feature extraction. Existing works only extract homogeneous features with a less effective backbone. We replace their backbone with our image encoder and our localized feature extractor. All networks after this improvement show an additional improvement in their own performance. Specifically in unseen classes, the inclusion of the localized feature extractor boosts the performance by a significantly large margin. In summary, local is a two-component novel system. It utilizes local feature extraction with composition classifier to make the correct object attribute association even with background clutter and interfering elements. In the three benchmarks, we outperform existing works. Moreover, our feature extractor is able to improve current works as it is modular and can be applied to any object attribute association method.